Welcome back to Science, Freedom, and Education. And we're going to be taking a break today from the biology textbooks, and we're going to be talking a little bit about black holes again. This was by request from a former student of mine named Nick. So, Nick, this one's for you. Today, we're going to be talking about the supermassive black hole that was allegedly photographed by the EHT team. It's in the galaxy M87. Which is supposed to be about 1,000 times more massive as the Milky Way. It's in the Virgo cluster, and uh, it's 55 million light years from Earth, so pretty far away. And what they had to do is, according to the article from sciencenews.org that I'm going to be reading from today, they had to use 8 different telescopes from all over the world pointed at this thing, trying to use computers to kind of make a collage, if you will. They had to take all of these different videos and pictures, and then they used a computer algorithm to stitch them together into a single picture that's been all over the internet for the last few months. This was announced in April. And if you look at it, if you see a picture of it, it looks kind of like a really blurry version of the One Ring from The Lord of the Rings. But this is what they're hailing as the first picture of a black hole. And what they did, if you understand the technology and stuff, that's impressive. The picture itself, not all that impressive. The casual observer is going to look at that and be like, okay, not really seeing much there. But anyway, I want to talk a little bit about the technicalities and some of the problems that I have with this. I do want to go back briefly to the last video, talk about some of the things that I talked about in the last video on black holes that I did. Just a reminder, number one, you have the paper from Dr. Laura Massini-Hoffman that showed that using the calculations from Stephen Hawking, the late Stephen Hawking, as a star collapses, it gives off energy. It gives off a massive amount of energy. And what she showed was that if you do the calculations based on every possible model that they'd come up with, a star loses too much energy, too much mass as it's collapsing to ever have enough to collapse into the black hole. And so what she said is that when they collapse enough to where they should have formed a black hole according to the science projections and whatnot, they're actually just going to go supernova. Now, some stars that don't have enough mass to do the ignition into a supernova will collapse and they'll form like a brown dwarf or a black dwarf or something like that. But when you have some pretty large stars, they'll have enough mass to collapse down, and what that does is it reignites all of the helium and whatever fuel is there, and it causes it to go critical, and that's where you get your supernovas from, and that's where you get your nebulas from, is these exploding stars. So according to Marcini-Hoffman, black holes are not possible that way. Also, we talked a little bit about gravity versus electromagnetism, and we're going to come back to that today. But just a reminder, the universal gravitational constant is 6.67 times 10 to the negative 11, and that is in units of newtons per meter squared per kilogram, or Newton meter squared per kilogram squared. And then you have very similar unit, but in terms of electromagnetism. And the electromagnetic constant is 9 times 10 to the 9th, and that is newtons meter squared per coulomb squared. And the difference there, of course, is the mass versus the charge. So, but when we talk about those constants as they relate to the force of gravity versus the force of electromagnetic, either attraction or repulsion, you have a difference, a ratio there of almost 135 quintillion. That is a lot of zeros. This is 18 zeros. And so it's an enormous number. And so to say that gravity, as that star gets further and further down, that gravity, which is the weakest of all the natural forces, is somehow able to overcome the electromagnetic repulsion of the stars, which we talked about. Stars are positive, like our sun has a positive net charge of 77 coulombs, and that may not seem like enough or a lot, but if you have two charges, each with a coulomb of charge, and they're only a meter apart, that's enough to lift 10 battleships, United States battleships, and that's 1 meter apart. We're talking in an inverse square law here. As the distance gets smaller, that force gets bigger by the square. And so, you drop that down to 1/10 of a meter, you have increased the force by 100. You drop it down to 100th, and you have increased the force by 10,000, and so on. So 77 coulombs may not seem like a lot, but a net positive charge means that star is never going to have enough gravitational force to collapse into a singularity where all the matter and energy are all occupying the same point in space. They're not logical from the known physics of the universe. So I just wanted to bring that back up. We're going to talk about that again when we get to talking about the black hole itself. I do want to point out one other thing. One of the things when I start teaching my classes is I try to show my students the difference between actual empirical evidence measured directly versus computer models. When you get into computer modeling, there's a lot of problems that can come up, and there's a healthy skepticism that comes with that, but it can be taken too far when you get into how powerful computers are and things we can do. I'm about to debate a gentleman who will use that the Earth is flat, and one of their main arguments is that NASA lies about everything, and everything that NASA puts out is computer generated and stuff, which is not true. But one of the things that you do have to be aware of is that you can do a lot more with computers because you can tweak them. You can manipulate data so that you get outcomes that are more favorable to your conclusion. And when you're dealing with a very complex hypothesis like the ideas of black holes or whatever, then trying to use 8 different telescopes synced all around the planet to try to take a picture of something that's 55 million light years away, that's a lot of complexity. And when you've already got your conclusion, when you've already said that what you're going to be looking at is a black hole in the center of a galaxy, when you take the picture, that's what you end up interpreting it as. I would like to just offer an alternative. One of the things that's been coming up in the last couple of decades is an electromagnetic run universe. The electromagnetic universe says that a lot of what Einstein tried to propose in relativity using gravity as the driver of the universe isn't correct. And we know that with quantum physics, there's a lot of things where Einstein's ideas are starting to break down. And so one of those two has to give. Yes, we don't understand a lot about quantum physics yet, but a lot of the things that relativity was supposed to bring us, we've had about 100 years or so of relativity, and it hasn't gotten much of anywhere. Yes, it was able to sort of explain a few things if we made some assumptions, but we're to the point now where relativity has had to assume so many things. It brought us Big Bang, but the problem with Big Bang is there's not enough mass in the universe, so we had to make up dark matter. 97% of all matter and energy in the universe is this imaginary dark matter, dark energy stuff that we don't have any evidence for other than it needs to be there for the Big Bang to be true. And that's where relativity has started to go, because Einstein focused on gravity. And that's not to say that Einstein was a bad guy or that he was stupid. He was a brilliant man. But his chosen pathway for studying science was gravity at the astronomical scale. And what we're starting to learn in the last couple of decades is that the universe is probably more driven by electromagnetism than gravity. Electromagnetism is far stronger, operates at the same scale as gravity, but is far stronger than gravity is, and is able to explain a whole lot of the phenomenon in the universe without recourse to making stuff up. So I'm going to suggest that the scientists that are doing that did the EHT project, I'm not going to attribute dishonesty to them. I think they are doing the best that they can with what they've been taught. I believe that they have, like every person, a bias, and so they are excited about what they've done, what they've taken a picture of, and they have seen a picture of what they think is their conclusion, which is this black hole. But I'm going to suggest to you that what they are seeing isn't what they are concluding that they see. There's a journal called the Journal of Nuclear Physics that has some fascinating ideas about how the structure of atoms are not what we think it is. We think when we're taught in school, when we see it in chemistry and physics textbooks, sometimes even in biology textbooks, when you see the nucleus of an atom, you see kind of the Chuck E. Cheese ball pit, where all of the protons and neutrons are just kind of this jumble of balls all up in a kind of a sphere-looking thing. What the Journal of Nuclear Physics proposes is that the nucleus has structure, and it's based on the electromagnetic properties of atoms as they correlate to the strong nuclear force. And so protons and neutrons and protons are attracted to one another through strong force over very tiny distances. And strong force over those distances is stronger than electromagnetic force over those same distances. But we're talking nanometers and less. And so what they have proposed is that the structure of the nucleus of atoms is an alternating ring matrix where you have proton, neutron in a ring, and then underneath that is another ring of proton, neutron, but it's offset by one. And what this does is it creates a kind of ring sphere where it bulges out towards the center, and it creates a little bit of an electromagnetically neutral hole in the top and the bottom where protons can be inserted if they enter at just the right angle. And through that, they're looking at doing some low energy nuclear reactions, what we would call cold fusion. So what I propose is that what we're looking at, and this is just a hypothesis, I don't know what it is that they're taking a picture of, and I'm going to read through some of the article here in a minute and show that they don't either. But what I propose that they're looking at is an electromagnetic event that is very much like the structure of the atom, because I think things in nature tend to repeat just on different scales. And so you have this center of galaxies that is an electromagnetic emptiness. It's a shielded region of space. Like when we talk about electromagnetic shielding in my physics class, how does that work? Well, if you have something that has got a negative charge on like you have a briefcase or something that has the surface of the briefcase has a negative charge, everything inside is going to feel an equal and opposite push in all directions. And so you have a net charge of nothing, and so you can store computer like data or something inside of the briefcase and not worry about it being erased. But anybody tried to hit that briefcase with an EMP, the stuff inside is going to be shielded electromagnetically. So what I'm proposing is that at the center of the galaxy, you have an intense electromagnetic field that exists there that is doing the warping that they're viewing. Electromagnetic fields will certainly warp light because light is electromagnetic in nature, and what we're seeing is a region of not a singularity, not a super compressed mass or whatever, but literally it's just empty space. and that you have a region of space where right there in the center of galaxies that the electromagnetic forces are so intense that it's creating a bit of a ring that the galaxy is, of course, around. We know that most galaxies are some form of a flat disk type thing, and that's what we're seeing. And the accretion disks, or the warping at the edges of that, are light being warped by the intense electromagnetic field, rather than some kind of an attractive gravitational field in an event horizon and whatnot. So something I want to explore more, something I want to see touched on by those who are dealing with the electromagnetic universe. It's fascinating for me, but as far as I can see it, as far as I understand the nature of singularities and black holes, they just can't exist. So let's get into the article a little bit here. I'm using some new video capture software here too, so we'll see how that works out. I'm hoping it'll record. So far, we're doing good. But anyway, they show the picture at the top of the article, and it says, "This is what a black hole looks like." We have seen what we thought was unseeable, and we've taken a picture of a black hole. And then a little bit later in the article, we've been studying black holes so long, sometimes it's easier to forget that none of us has actually seen one. So you can't see a black hole according to the model, because black holes don't emit visible light or anything. Actually, the gravitational well is supposedly so strong that not even light, which is the fastest thing in the universe according to relativity, is not able to escape it. And of course, there's some issues with that. I don't want to go into them tonight, but even relativity isn't consistent on talking about the speed of light, if you really look at what Einstein said about it. But so anyway, they said it's a Herculean task what we've done, because black holes are notoriously hard to see. The gravity is so extreme that nothing, not even light, can escape across the boundary at a black hole's edge, known as the event horizon. But some black holes, especially supermassive ones dwelling in galaxy centers, stand out by voraciously accreting bright disk of gas and other material. That means there's this edge right outside the the black hole's event horizon, allegedly, where the light is moving really fast, and it's able to reach escape velocity, because it doesn't quite cross into that event horizon. And so we see that these super hot gases and these jets and all of these things. Of course, the speed of light is supposed to be a constant, so how light would move faster than C anyway, they're not really consistent with that, or they're not really explaining it very well. But anyway, they go on and they talk about the hype and the build-up, and they talk about all of these. They're very excited about it anyway. But anyway, it says the image aligns with expectations of what black holes should look like based on Einstein's general theory of relativity, which predicts how space-time is warped by the extreme mass of a black hole. So this is where they attach it to Einstein's general theory of relativity. That word space-time there, that's been around for only about 100 years. The argument is that space and time are the same thing. I disagree with that. But I don't want to get into it in this video. But they they say that this is one more strong piece of evidence supporting the existence of black holes. The problem that I have with this is that they give us this picture. There isn't really all that much to the picture. Now, the technology and the feat of taking the picture is cool, but the amount of data that we got from it isn't. They're kind of jumping the gun here with it. They're moving into conclusions without actually giving us any of the evidence. So they're assuming that it's a black hole, and then they're saying that this is evidence for black holes. Okay, well, you still have to get past some problems. And so I want to address some of the other things that they say here. First of all, they say black hole environments are a likely place where general relativity would break down. Well, if general relativity predicts them, and then general relativity breaks down. Number one, general relativity is not a law of the universe. It's not a universal law. It's just a really trumped up hypothesis that uh, has gotten some data to kind of back it up, but it's also got a lot of flack in the last few decades. And one of those is with the kind of the breakthroughs that we've had with quantum mechanics. And quantum physics and relativity do not get along at all, because quantum mechanics is the really, really small. Relativity is dealing with the very, very large, the astronomically large. And so the quantum mechanics, when you get down into the singularity size of things, singularities are supposed to be all of this mass occupying the space less than the size of an atom. Well, now you're in the realm of quantum mechanics and quantum physics, and relativity and quantum physics they're like siblings that hate each other, or a married couple that just don't get along, and uh, it's awful, like how the physics work together. And so to say black hole environments are where general relativity breaks down, but black holes are because of general relativity, that's approaching contradiction territory there. So that's one of the huge problems that I have with it. The other is, it says, so testing general relativity in such extreme conditions could reveal deviations from Einstein's predictions. Well, what do you do when you have a hypothesis that you don't get the results that you predicted? You throw it out. What they're actually doing here is, if this is relativity rather than electromagnetism, if this is gravity, what they're doing is they're disproving the hypothesis. And so if they're disproving the hypothesis that general relativity is, then this isn't a black hole at all. And so it's really, really hard sometimes for a lot of people to read this and to digest it. You really kind of have to, I guess, practice at it. And this is where I think the education system has been breaking down, is we are not teaching our students to disagree appropriately, to give them information that is flat out wrong, and have them do the experiments, and have them not only be able to tell us this is wrong because, but to not be afraid to. That's one of the things that I tell my students. I make mistakes all the time. I am by no means an unflawed individual, and if they bring up a mistake in class, let's explore it. And if I made a mistake, I admit it. I make a big deal out of it, because it's important for them to understand that as a scientist, I am not flawless. I am not some form of clergy that they just take my word as some kind of gospel truth. I make mistakes. And students in our education system must learn, again, the true critical thinking skills by being shown what it means to break down something like this and disagree with it, not by calling names, not by ad hominem attacks, or well, this person says or that person says, the ad veracundium things that so many are guilty of today, but by saying the evidence just isn't telling me what you're telling me it's telling me. If you're showing me this picture and you're saying that's a black hole, prove it. Well, but this is proof of a black hole. No, what you have is a fuzzy picture that looked like it came from Lord of the Rings. I need a lot more than just this news article. I want to see the data. I want to see the evidence. Stop throwing it out there as if it's something that's too hard for me to understand, because it's not. And then I'm not talking about me specifically, but I'm talking about the public. If you throw out the information, the people will rise up to that standard of understanding. This is what I have to do with my students. I don't dumb things down for them that I don't have to. Sometimes we have to take things a little bit slower. Some things are complex, but I don't dumb it down. I don't put it in such easy terms that suddenly it's meaningless. It's worthless. So raise that bar, put the information out there, link to the research journals so that we can actually examine, why do you think this is a black hole? Oh, you're telling me that this is going to, that the very foundation of what gave us black holes as a concept breaks down when we take a picture of that? Well, that's contradictory. You're going to tell us that the data that we're getting back is going to show us that there's deviations from the hypothesis. Well, that means that the hypothesis needs to be thrown out or reworked or something. So that's what I'm getting from this whole thing is they don't really know anything new. They just took a pretty picture. It's a really cool picture. It's a picture of the center of a galaxy 55 million light years away. That's awesome. That is a really cool thing. The 8 telescopes from all over the Earth, they turned the Earth into a big giant telescope is what they did. And that is fantastic. Not knocking that at all. But the conclusion that they took a picture of a black hole, I don't have enough data to make that conclusion from just the picture and from the things that I know about gravity and electromagnetism. That the paper that Laura Mercini Hoffman did was pretty solid. Haven't seen anybody come back and explain why she's wrong yet, and that was in 2014. I just don't have enough information to make the same conclusion that they do, and it's just not something that I'm ready to step out and say I was wrong. Yes, black holes do exist or whatever. I don't have. They're not giving me anything to make me change my mind on this. So there's a little bit more to the thing. They really get into kind of the technicalities and stuff of it, but just remember this was a lot of computers putting this together, stitching this together, taking a picture of something that was really far away, about something that they admittedly don't really understand too much. So it's cool, but it's not all that. It's not black holes. Definitively, it's not black holes in the sense of, yep, that's it. There's, I know the Earth exists because I'm standing on it. I know I exist because the evidence is there. I know a lot of things because of direct observation. I know the sun exists. It's in the sky. I see it every day. Those types of things are directly observable. This is not there. This is a lot of inference and a lot of logic and a lot of computer modeling and a lot of wishful thinking on a theory, not a law, but a theory that has come under a lot of fire recently. And I really, really encourage a lot of people, if you really like the physics of this stuff, go look at the electromagnetic universe. It is fascinating, the things that you'll find there. No requirement for a Big Bang, no requirement for dark matter or dark energy, no requirement for any of the things that they've made up over the past 10 or so decades to explain how we got here, by making stuff up. And it's pure physics. I'm not trying to, we're not getting into the religious realm. These videos are not for that, but the idea that we have to make stuff up to prop up our hypotheses is not good science. That's bad science. And so I would like for us to be more evidence-based, less scientists say so based, and that's what we need to be teaching the students. We really need to get back to some good hardcore critical thinking. One of the things I plan to do, I'm going to be teaching physics again this year. It's coming up. Brand new school. One of the things that I'm going to be doing a lot more of is discussions, and I'm going to be giving my students information, and sometimes I'm going to tell them this information is wrong, but I'm not going to tell you how it's wrong or why it's wrong, but you have to use the information that you already know and the information in whatever article or video or whatever that I show them. You have to use that information to tell me why it's wrong, and be able to disagree with it and really break it down and not be afraid to throw stuff out and say, I think it's wrong because of this. And I think that's what our students really, really need these days. You can see it all over the United States. You can see it all over the world. People just don't know how to disagree anymore. They don't know how to do it logically. They don't know how to do it critically. We're just yelling at each other, talking past one another, and that's not useful. So thank you for joining us. The next video I do will probably get back to the biology textbook for a little while until I take another break to do another requested video. Thank you, Nick, for making this request, and we'll hope to see you guys next time.